Hello, we are continuing our video lecture series on section 3.3 in the Lock 5 textbook. Okay, so we're looking at sampling distributions and bootstrapping. So ideally we'd have a population, and we want to know something about the population, say the mean, what measure of the center of some population. And if you took samples from this population, they should hopefully stay fairly close to the mean if you have a good sample, but they are going to kind of spread out. So we don't see the tree or really all of the seeds. In practice, we really just have one sample most of the time. So what are we going to do with this one seed? This idea of bootstrapping is to take this one seed we have right here. So we're going to call that an X bar because it's a sample statistic, sample mean. And we're going to grow a new tree with this idea of bootstrapping, with this bootstrap, quote unquote, population. So what we're going to do with this one sample is estimate the distribution variability of the sampling means from these bootstraps. So all these bootstraps sample means will be computed from just this one sample mean. And hope is we will capture the true population mean somewhere in this sampling distribution, bootstrap distribution spread. So kind of one way to think about bootstrapping is bootstrapping statistics are to the original sample statistics as the original sample statistic is to the population parameter. So the drawback is that for a true sampling distribution is centered around the population parameter. The bootstrap distribution is centered around which of these four? And it is centered around the sample statistic. So ideally, by itself, this is not good because we want to know about the population parameter. But we actually don't really care too much about the center of these bootstrap distribution. We care about the variability. That's what we're going to use with these bootstrap distributions. So the variability of these bootstrap statistics is similar to the variability of the sample statistics. In other words, we can use the standard error of a statistic can be estimated using the standard deviation of the bootstrap distribution. So we're going to take a sample instead of the population, take one sample. From that sample, we compute the statistic, the center. But from the sample, we're going to create a bunch of different bootstrap samples. And remember, all these bootstraps are samples of the same size of the original sample, and they are computed from the sample via random sampling with replacement. From these bootstrap samples, we're going to calculate a statistic from each bootstrap, and then we can compute or display these statistics in a dot plot. And then from there, we could create a standard error, the standard deviation of this bootstrap distribution. And from there, we could then compute a margin of error. 2 times the standard error will be the margin of error. And then we're going to add and subtract that to the original sample statistic to get our confidence interval, our bootstrap confidence interval. All right, let's look at an example. We've got a sample below here. We're looking at original sample. We had 100 Reese's Pieces, 52 of which were orange. And we want to generate a 95% confidence interval for the true proportion of Reese's Pieces from this data. All right, and the correct answer is B. So how do we get B? We take the sample statistic, 0.52, that's a p-hat, add or subtract 2 times the standard error, and that standard error is right here, it's the 0.05. Okay, what about other parameters? We're going to estimate standard error and confidence intervals for proportion, difference of mean, difference of proportions, standard deviation, and correlation. So in this chapter, we're going to focus on all of these except the standard deviation, but we will look at proportion, difference of means, and correlation. And we're going to generate samples with replacement, calculate sample statistics, and repeat. So we can use bootstrapping to assess the uncertainty surrounding any sample statistic. If we have sample data, we can use this bootstrapping technique to create a 95% confidence interval for any parameter. Well, almost. We'll talk about that in a second. Okay, used Mustangs. All right, so you want to know what's the average price of a used Mustang. We could select a random sample of 25 Mustangs from a website, AutoTrader, and record the price for each car. The price will be $1,000. So here we have a sample of 25. So this is gathered from the AutoTrader website. And what we're going to do is plot this. We have a dot plot of all the selling prices, the used selling prices, 25 cars. The sample mean, X bar, 15.98, so about $16,000 a car. And we have a standard deviation of this one sample is 11.11. So our best estimate for the average price of Mustang is around that 16,000. But how accurate is that estimate? Another way to formulate this is how much variability is there in the sampling. All right, so we can do that with the approach of bootstrapping. So to get a visual of what we're doing, we've got the original sample right here. To create one bootstrap sample, we're going to pull one car from the sample, but then we're going to put it back, reshuffle, pick again. So notice we get the same car twice, but the sampling has to be the same size, and it can only include data points from the original sample. So we got one bootstrap sample. We can calculate the mean price of this new bootstrap sample and repeat many, many, many times. So here we have StatKey has computed that for us. We've got the original sample right here, 15.98, 25, and we've got 2,000 dots in here. These are 2,000 different bootstrap samples. And we're going to focus on the middle of this is going to be about the sample statistic, sample mean, but really it's that standard deviation. That is the key part. This is what we're going to use as our standard error, 2.178. So what I'm going to do before we go on the slides is I'm going to go over to StatKey, and we're looking at confidence intervals for single mean, median, or standard deviation. And we actually have a Mustang price is already entered in, prepackaged data. So I have the same data I showed you on the slide. N equals 25, mean is 15.98, standard deviation is 11.114. So to take one bootstrap sample, generate one sample, there we got one dot. So notice the mean is higher. We got 17.198. And that's because we randomly pulled samples from this original sample with replacement. So we ended up getting some repeated high values to get this higher mean. I could take another sample, and as I take more and more bootstraps, notice the mean on the bottom is changing. It should get closer and closer to the 15.98, but it's that standard error. That's the important part. And let's generate 1,000 samples, and let's do 2,000. So we've generated 2,008 bootstrap samples from this original sample of 25 Mustangs. So notice when we did this, I got a standard error of 2.198. This is the standard deviation of the bootstrap sample. We're calling this the standard error. So it's not the exact same as we have on the slide. We have 2,000 samples, it's 2.178. So the standard deviation or the standard error of these bootstrap samples are going to differ because there's some variability and randomness in how we pick these bootstrap samples. So as a reminder, that 95% confidence interval is computed by taking the statistic and adding and subtracting 2 times the standard error. So for the slide, the sample statistic is 15,980, plus or minus 2 times, and we're going to go with the slides standard error. It was 2.178. We have to multiply that times 1,000. Add and subtract 2 times that to get our 95% confidence interval. And we'd say we're 95% confident that the average price of a used Mustang on autotrader.com is between $11,624 and $20,336.